Good morning, everyone. Welcome to Physical Chemistry 4. We are in the chapter on Hückel theory. And last week we introduced this theory, and I'd like to briefly recapitulate what we talked about and then proceed with the topic of bonding within Hückel theory. And afterwards, we'll also have a little couple of slides for the topic of the matrix notation. So you can see that table of contents up here. Now, just to recapitulate, we presumed that here in equation 1 that our wave function can follow a product ansatz, and this product ansatz is done in terms of molecular orbitals, right? Phi I. These molecular orbitals cover the entire area in which your molecule is. And then in point 3 here, you have the ansatz that any one of these orbitals is a series expansion in atomic p orbitals, right? That's what's written in equation 3. And so our task is to see what is then the energy with this ansatz. So this small ei, right? These eigenvalues of the orbitals, which sum up to the total energy of the pi system, and also the coefficients which would define each orbital. Okay. So in point 4, we discussed the normalization. And we found that the sum over the coefficient squared for any orbital always has to be 1, right? So you have to impose this normalization for every orbital. And then we use the variational principle, as you recall, to arrive at a secular equation. So taking this derivative, so insertion here in equation 7 to 10, we simply inserted the series expansion. Then we applied the variational theorem and arrived at what you know already in terms of a secular equation. And so you see this would be any row going over I, right? The small I here. And you do this to establish a system of equations, and here you see the example of ethylene. And then maybe the most important equation then is really here in equation 19, where you see the matrix of the Hamiltonian elements and the overlap in elements, right? And these two matrices within Hückel theory, the elements in these matrices are being approximated as constants, or being 0, or being so small that they can be truncated, right? So that's what Hückel theory embodies. So the secular equation means that this determinant has to be 0, right? And from this condition here, right, also written here, you see that we can, there are no coefficients, so you can get the n eigenvalues just in the basis of your p orbitals on each atom. You don't need the knowledge of the molecular orbitals to predict the eigenvalues of your electronic pi states. Okay. So now comes the Hückel approximation. So if you wanted to evaluate this determinant, of course, we need to know what is H and S. And so here you see these approximations. So if the orbitals sit on the same atom, then it's always the same number for any given chemical element. If they are neighbor, then they have the same value beta for any pair of chemical elements, okay? And this beta value can be of the order of 75 kilojoules per mole. And then the most severe approximation, very crude, is that we assume that the overlap is negligible for neighboring atoms and even atoms being further away, right? So this is a dramatic and horrible approximation, but it makes our problem easy or much easier to solve, right? And so here's the example with ethylene. We can then write our determinant like this, and then you can easily solve, and you find you find two solutions to these this characteristic polynomial. One is the HOMO eigenvalue and one is the LUMO eigenvalue, right? And now please remember, many students make this error. They calculate the eigenvalues correctly, but then they fail to calculate the total energy of the pi system. This is, of course, the Aufbau Principle. So if you have two electrons, like in ethylene for the pi system, then these two electrons occupy the lower orbital, right? So you have to count that eigenvalue twice. And so this is, you have to fill up the shells following the Aufbau Principle, right? All right. So once you have these energies, right, you solve this determinant here. You then want to, as a next step, to get the orbitals, right? And the goal is really one of the typical goals, or the main goals, right, is that you have some kind of MO diagram, right? Let me draw something. So this could be an MO diagram of a system with just 4 electrons, okay? But apparently you have 6 states, so you must have 6 atoms with p electrons, with p orbitals, okay? So something with 6p orbitals could be, for instance, something, a molecule such as benzene, but you remove 2 electrons, right? So benzene 2 plus. This could be the MO diagram of benzene 2 plus, right? Now I have to add to this. Just this is not yet an MO diagram. This is just the energy diagram, right? The MO diagram is that next to each level, you would make some drawings of orbitals, right? So I'm just inventing something now, but now you have an orbital drawn next to the state. And if you do that for every state, right, then you have what is known as the MO diagram, right? So you can also denote the states or the energies, right? if you have 6 eigenvalues, right, you could denote these energies. And so this is a typical way how to draw these MO diagrams. We'll discuss another example in a second again for benzene, right? But this idea is that the procedure consists of first solving for your eigenvalues and then populating your these eigenvalues, right? So you first get these lines and then you populate them with the electrons you have, right? This is typically part of the question that the system is specified, right? And then once you have that, then you have to ask, okay, how do the orbitals look like? That's the subsequent question. You can only address it once you know the eigenvalues, because you need these eigenvalues to substitute things back in this equation number 19, right? This is equation number 19. 17 and 18 exemplify number 19 for the 2-electron system. Now, when you insert this back, of course, you do this insertion back using the Hückel approximations, meaning your overlap matrices and your Hamiltonian matrices assume the values of 1 for the overlap on the same atom and beta and alpha. Okay, so this is what you see now here, right? For ethylene, and then you can insert your eigenvalues here, and you can solve for your coefficients. Okay, and so you find then for every eigenvalue, of course, you need to find a set of coefficients, right? So every eigenvalue has its own molecular orbital that's associated to it. So in this case, we have only 2 orbitals. One will be the HOMO, occupied by 2 electrons, and the other one will be the LUMO. Right? Now, because you have only 2 equations and 2 unknowns, they determine each other. It's fully determined up to a scaling factor, right? So we cannot resolve our C1 here. We only get the ratio between the 2 coefficients. And we have to use the normalization constraint here to fully determine then all coefficients, right? So the procedure is that you first insert the eigenvalues from your secular, from your polynomial. You insert that in your system of equations, and then you solve for the coefficients for each eigenvalue up to 1, right? You have to substitute them until only 1 coefficient is left, and then you can determine this last coefficient by normalization. The full wave function then is the product of these 2, and the electron density is the square of that. And so here this is shown in the atomic p orbitals of the 2 atoms. Right? Now we then discussed a couple of examples. So butadiene looks like this. You can do this trick that you use the rank of your matrix and as an exponent for beta, and then your matrix typically simplifies in this way. And then you see here the energy spectrum, right? These eigenvalues that emerge, and you can set this into your system of equation for butadiene, right? And then in this case, you will find these coefficients here. Right? So it's exemplified on these slides, and then for the other orbitals, you can repeat this exercise, and I strongly recommend you to do this exercise as well as the exercises with Mr. Trestman. It's very important that you practice this, because this, of course, is a typical question in the exam, also to demonstrate that you understood the whole concept of this course by producing the correct numerical numbers for the Hückel solutions of any given system. Now, I was asked also last week if the slides could be uploaded to Adam, and I did that, so you should find the PDF slides there, so you can verify your solutions with respect to the numbers indicated in equations 42 to 44. Now, it's very important to also then consider systems that include cycles, right? So the pi system is intimately linked to the question of aromaticity, and it is one of the great accomplishments of Hückel, that his theory does account for aromaticity, right? And it does so by virtue of coupling the secular determinants through these off-diagonal elements here that close the circle, right, in your molecular structure. And it is these elements, right, that introduce the additional gain in energy which you can expect through an aromatization or a closing of the loop, right? So as demonstrated here, we can find the eigenvalues, and if you sum up all the occupied lowest lying energy levels for 6 electrons, you find 6 alpha plus 8 beta, and this means that you have 2 betas on top of what 3 ethylene molecules, 3 separate ethylene molecules would get. Right? If you insert these solutions into your system of equations, your 6 equations for the 6 eigenvalues, right? So in total, 36 equations. You should find, thanks to normalization, then you should find these molecular orbitals. Please also at home try if you can reproduce this. Right? You should really practice this. Right? You can also try other variants of benzene. Right? You can substitute them. You can try pentadiene, cyclopentadiene, right? You can also try cyclohepta, triene. So these are all questions, right, which you might want to look at. Now, this is the picture here. This is what we are referring to when talking about a molecular orbital diagram. So if somebody asks you to produce a molecular orbital diagram, this is what is expected. Again, an energy axis, the indication of all the eigenvalues, the indication of which levels are populated, and the molecular orbitals that make up the solutions to Schrödinger's equation for each of these levels. All right, before we now go to bond order, this was our brief recap. Is there any question? It all seems pretty clear. So let's now look at what we can do with our solution to Schrödinger's equation, right? And this solution is really manifested in the set of coefficients which we have, right? And in the eigenvalues which we have, right? So let's look at what we can do with this. So we can consider the total energy, right, which is the sum of the eigenvalues times the occupation number, right? So if we now consider the eigenvalue I, right, it contains the Hamiltonian and our molecular orbital, and this is our solution now. Now we presume we know these coefficients, okay? You solved the secular equation, you got the eigenvalue, you inserted it in your system, now you know these coefficients. Now what you see is that you can write this due to this double summation, right? You can write this as your sum over your alphas, right? Plus the sum over the betas, right? You sum here over atoms R and S, right? And the beta guys, right? These are your neighboring atoms, right? So the alpha guys only survive for the same atoms, right? This is why one of these sums has died, and your coefficients are squared now. And here you have the neighboring, these are neighbors, R and S with the beta, right? And so we can see that these number of electrons, right? When we want the total energy, right? We have to still sum over number of electrons, right? So if you insert this expression here for EI, then you get the sum over atoms, right? And we exchange the summation ordering, and all of a sudden you see your total energy as the sum over all atoms. Each atom has this alpha, and then it's weighted by the sum over your coefficient squared multiplied by the occupation, right? Now, this is not equals 1, right? Because the unoccupied orbitals in your coefficients, they will not contribute here, right? Their n here will be 0, right? And then you have this double summation here as well. And also here you can pull this beta out. And this goes over all the atoms that are neighbors, all atom pairs that are neighbors. And here you have, instead of a square, you have the product of the coefficients of the two neighbors times the occupation number from that eigenvalue. Okay. So this means basically you're projecting. You have all these different states, right? And as you go through each atom, right, you sum up all the contributions from the different states for that atom in this first summation. And here in the second summation, you go through all pairs of neighbors, right? And for each neighbor, you sum up the product of the coefficients from all states, right? So you project all your states, the entire spectrum, down onto your one atom or that atom pair. And so these coefficients, right, they correspond to your wave function, right? And the wave function corresponds to your electrons, right? That it represents your electrons. So that is electric charge, okay? And so what this really means is that these coefficients here, when you sum them up, that's the total electronic charge sitting on your atom, okay? So that's this QR here, right? It's also written here, where your QR corresponds to the charges of all the molecular orbitals, or the occupied molecular orbitals at atom R. And this P here, right, is this double summation. This corresponds to the charge of the bond between atom R and S. Okay. So let's exemplify this. Okay. So for butadiene, you can now consider, so butadiene, remember, you have a double bond, a single bond, and a double bond again, right? So it's interesting to look at the bond between 1 and 2, and the bond between 2 and 3. The bond between 3 and 4 is going to be like the bond between 1 and 2, right? So we don't care about that. So in butadiene, we had these coefficients. Let's go back to the example, right? This was the example of butadiene, right? So remember, we had this coefficient, 0.372, 0.602, 0.602, right? And then 602, 602, 372 on the first atom, right? And on the second, 0.6, here again, the product of these and these is going to be the same. And we only occupy the lower two, right? So once we have the product of these two for the 1,2 bond, and for the 2,3 bond, we have the product of these two. That's different from the product of these two, plus the product of these two. And now we get a negative sign here, right? So this would suggest that the electron density in the single bond, in the 2,3 bond, is lower than in the 1,2 bond. Now let's see if that's true. So here we have 2 times this, right? 2 electrons that sit in the first one and 2 in the second, right? So in total we have on that bond 0.894, and the 2,3, right? We have the corresponding equation, right? Here there are no electrons in the higher orbitals, right? That's why the zeros are there. And here you have your change of sign, right? Sorry, so in equation 65, you have this change of sign in the second part, and hence our the number of electrons in that bond is reduced, right? Now, to estimate the bond order, you would still have to add the single bond information, right? So for the total bond order, you still have to add 1 for each single sigma bond. Thus, according to Hückel theory, the CC bond orders in butadiene are 1.9, right? This is roughly 0.9, and 1.45, respectively. Right? So this is the interpretation of these electrons in between the atoms, right? In terms of this P. That you can use this as an estimate of the bond order. Now note that as you can see here, this bond order, right, is just a distribution of electrons. It's not an observable, it's not an operator. We are simply using our coefficients to estimate where the electrons are, right? We also estimate where the electrons are on the atom, right? That's the charge. Right? How much charge do you have on each atom? And so it's really important for you to realize that the chemical bond, as we talk about, is basically an object which we can calculate something, right? We can interpret it, but it's not an observable as such, right? It's just these coefficients that sit there. We do not have an operator that directly spits out the bond, right? But rather we have this implicit in the solution of Schrödinger's equation. We can see how the electrons change, right? And these changes in the electron distribution, they are for real, right? Your electron density is an observable, right? So changes in electron distribution, changes in energy, these are well-defined concepts. The bond in itself is not. All right, now it's interesting. You can relate the bond order with structural changes. For example, you will find in diverse cyclic carbohydrates, right? If you calculate the bond order, you will find that in comparison to the equilibrium bond length, there is a clear correlation, right? And basically, the smaller the bond length, right, the more of a double bond character will you have, right? So the Lewis graph picture, right, that it's either a double bond or a single bond, is of course way too binary for reality. That's basically a sort of truncation towards the integer values. Hückel theory already tells you that these are fractional numbers or trends, right? And so you shouldn't be surprised to not see here a step function from 2 to 1, but rather a smooth transition. All right, this is now what I wanted to say about bonding and the charges and the coefficients. And I'd still now like to briefly talk about the matrix notation, right? So as you know, and to some degree, we already noted down this matrix notation at the end of the Variational Theory chapter, but I also wanted to still conclude Hückel theory with this as well. So the secular determinant really results from this matrix eigenvalue problem here, right? And this equation here, I hope you see this, is identical with this, right? You basically factor out your C, and then you put the E as C on the right-hand side, and then you have that expression, right? Now, you can you can denote these coefficients and the EAs. You can view this, right? EAs being this, so S, right, vanishes. It becomes a diagonal identity matrix within Hückel theory, right? And then you basically have the expression for something like Schrödinger's equation in matrix notation, right? So the C are now simply your eigenvectors and eigenvalues of H. Now, you do this for every state, right? So this means you have a whole matrix, and you can put into this matrix the normalized eigenvectors of C, and then you obtain this relation where D is simply the diagonal matrix with the eigenvalues EA on the diagonal, right? So you can also write that matrix in general with this element where any off-diagonal term you have a Kronecker. Now, if you define an occupation number, right? So in the sense that you would like to recover your total energy, right? Then you would need to account for the occupation. Then you can simply do this where the occupation number is on the diagonal, and on the off diagonal, you switch this off, right? So you can define this matrix, and then you can sandwich it into your eigen vector matrices, right? And that will spit out another matrix, and you can try this by going back to the bonding part, but basically this R matrix has the charges on the diagonal elements, and on the off diagonal elements it will have the bonding information, right? These P elements, right? So if you wish, on the previous slide, that's effectively what you've been doing here, right? And then we can define a diagonal matrix A, right, where on the A we put our alpha coefficients, and a matrix B where on B we put our beta coefficients. So the HAA, the Hamiltonian matrix AA for our alpha is on the diagonal, and on B you have the beta for all neighboring atoms, and then you will find that the total energy of the system is the trace of this R matrix times the A matrix plus the trace of your R matrix times the betas, right? And that is really the same as your R matrix times the Hamiltonian matrix. So for example, for ethylene, right, you will find for the R matrix this, and then this is your Hamiltonian matrix. And so if you multiply this out, you get this, and you take the trace, you have the energy of ethylene. Okay, so this matrix notation slide, right, there's no new insight here. It's basically to assist you in the bookkeeping of the equations, right? So if you wish, this last slide is the essence of the entire Hückel chapter, right? It integrates your coefficients into your R matrix, your eigenvalues and energies into the A and B matrix, and it spits out the total energy as a result. With this, I'm at the end of the Hückel theory chapter. Is there any question at this point in time?
Yeah, I do have a question actually. About could you go back before, I think the last slide before matrix notation?
This one?
Yes, yeah. I think I don't find the connection between the coefficients and the charges on the bonds.
So you mean equation 61?
What you did between 62 and 65, you put in the coefficients. I'm not sure what's the connection between the coefficient and the charge.
You see the PRS. So our energy is the sum over all pairs, okay? And each pair contains the beta value times the weight from these coefficients, okay?
Oh, it's the weighting. Yeah, that's true. Okay.
That's right. It's this sum here, right? In equation 60. And equation 62 is basically writing out the sum for ethylene for the first bond, for the 1,2 bond. Does that make sense?
Yeah, that's why only 1, 2 are non-zero.
Exactly.
Okay, and this. Okay, I think that makes sense.
So let me thank you so much for asking this. Let me quickly give you a little drawing on So this is butadiene, right? And on I'll make a little drawing so that it is more clear what's happening here. So basically, we have contributions from the p orbitals.
Are we supposed to see what you're drawing?
Not yet.
Oh, okay, good.
I show it in a second. Okay. Show you this. All right. So this is the orbital, the molecular structure. And these are the two lowest orbitals with the coefficients which you see on the shared slide shown in equation 41 and 42, right? So first we have a small contribution, then a big one, then a big one, then a small one in the first orbital. And then in the second orbital, we have a large, a small one, and then of opposite sign, a small one, and then a large one. Okay? So this is how the two orbitals look like, phi1 and phi2. Okay? And now we are interested in looking what's the contribution for, and now let me draw this in. So we have atom 1 and 2 and 3. Okay? So we have a P12 and a P23. These two guys. And so if we go now here, you see in equation 62, we're getting twice the coefficient of C11 and C21, right? And twice the coefficient of C12 and C22. So this is 0.3 times 0.601 and 0.602 times 0.372, right? And in each we have 2 electrons, right? And so our p pi, right, we get a contribution from the product of let's see one. Here C, this is C11 times C21, right? No, sorry, this one and this one, and this one and this one, right? Those are the two. Their products we add up here, right? And then we add up this product, 0.601 times 0.601, plus this product. And here you have the change of sign, so you effectively subtract something. Does that make sense?
Sorry, yeah, that does make sense about the coefficients. So the first orbital would be, what did you say that would be C1? And the second?
So this is my first atom, right?
Yeah.
And this is my first orbital. So this is C11.
Okay, yes.
Right? And this is my second atom and my first orbital. So this is C21.
Mm-hmm.
Right? And then I add the product also from the next level. So this is C22 and this is C12.
Okay.
Sorry, this is C22 and this is C12.
What's the first one? Can you say that again? Just the last one you'd mentioned right now.
This is
That'd be
C22.
C12 would be
Equation
that one.
62. And this is C12.
Where the 1 would be the atom and the 2 would be the level. Like the phi.
The first one is the atom, exactly. And the second one is the orbital.
Orbital, exactly. Okay, good. Thank you.
No problem. Thank you so much for asking this, right? These are exactly the you have to stick with one notation, doesn't matter which one, it just has to be consistent. But this is the kind of understanding you have to get. All right, so it's already past 11. Let's have a little break and resume at 11:15, okay?
May I ask something? Or
oh, sure. Yes.
Later. If you wait a minute, I have you on the big screen and I have to figure out how to get the slides back. Yes. I mean, you said now we have the result of this is that we have 1.9 bond order for 2 bonds and a 1.45 bond order for the other bond, right?
So you have, if you ask about the bond order of the 1,2 bond, okay?
Yes, and
then you get
1.9.
From the Phys system, you get 0.894. And from the sigma bond, you would add a 1. So you have roughly 1.9 for this bond.
Yes, but what I actually wanted to ask, I mean, this adds up to like 5.25. Does this mean that the carbon hydrogen bonds like have on average a bond order of 1 point something? I mean,
the carbon hydrogen.
Yeah, no, I mean this doesn't add up to the wait a minute, should have thought more before I asked this.
No problem, just ask, don't worry. Tell us what you think.
I mean, in the bonds we're looking at, there should be a whole number of electrons, and this doesn't add on to a whole number of electrons.
No, this is not true. Okay, you have the bonds, but you also have the charges, right? So in this discussion, you also have to take your Q, these QRs into account, okay? And once you add those up, when you add up all your coefficients, then you recover so for each molecular orbital, these coefficients normalize to 1, right? So then the total number of electrons is simply your occupation number times these charges, right? Times these coefficients.
So there's just some charge sitting on the atoms that do nothing in the terms.
Absolutely,
of
absolutely.
Oh,
yes.
thank you.
Most of the electrons, remember the pictures we drew in the beginning, right? Most of the electrons sit on the nucleus. Right? It's just that in this case, we can nicely project out the cross-coupling term in between the atoms to estimate how much of the charge goes in between. Right? All right, so let's have a break and we resume. Okay, now it's already 11:05. Let's resume at 11:20, please. All right, let's continue. I would like to enter now a new chapter for this course, and this chapter is Hartree Fog Theory. Okay. Now, also here I will make use of slides. So let me the slides, and I will share these slides also. I will upload them on Adam as well. So this is our 7th chapter, and this chapter is equally important, I think, as the chapter on Hückel. It will bring you closer to what actually is more commonly used level of theory. And so I would also like to urge you to pay good attention now. Let me share these slides. So yeah. What's great here? Okay. So Hartree Fog is now a theory where we would like to be more general than Hückel. Okay, so this goes beyond merely describing p electrons and which assemble, which unite in a pi orbital. We want to now treat all electrons on the same footing. Okay, no matter what is your system, no matter if you have p or pi or sigma or d or whatever orbitals, this is briefly to motivate also the procedure where you will find reasonable results. Okay, so when you wonder why we would need still Hartree Fog, right? So of course for the hydrogen atom we know the exact wave function, right? But for helium, actually for any hydrogenic atom you can get the exact wave function, but for helium, lithium, or H3 plus, so already with just 2 electrons, things get more tricky, right? Remember I showed you the numbers for calculating the energy of helium, but still we can get very decent wave functions numerically, but as we go beyond, right, for atoms and molecules with many electrons, then meaningful wave functions are more tricky and too expensive, and so the Hartree Fog theory has been devised to get us something more realistic. So this is still an approximation. So the Hartree Fog theory neither accounts for non-adiabatic effects. So, for instance, surface crossing. This is related to the Born-Oppenheimer approximation. Nor does it account for heavy nuclei, where your electrons have such high kinetic energy, such velocities that they do approach the speed of light, and so then that changes the mass of your nuclei, right? So you have these relativistic effects then, right? So the Hartree Fock still does not account for that. And also it will not account for quantum behavior of your nuclei. So light nuclei can tunnel. That is, of course, the at the origin of the kinetic isotope effect, and this is not something the Hartree Fog theory will take care of. It is really a mean field theory. That is, every electron interacts only with the average from all the other electrons, right? So it's not as if the electrons would not see each other, but they see only the average from all the other orbitals, if you wish, right? They cannot, one orbital might have a much stronger effect than the other, and that would be smeared out, and that is averaged out. And so you do get, when one orbital is, let's say, governs your process, then you're running into trouble with Hartree Fock. So polarizability, conjugated system, transition states, London dispersion, this is a problem for Hartree Fock. So here the approximation will not be very good. And then there's also the so-called single reference problem, right? You will see this later on. We will make use of a determinant, which is known as Slater determinant. And this will be basically your wave function. And this is problematic because for states that are linear combinations of multiple possibilities and multiple options, multiple electronic configurations, right? Then you would require multiple determinants. So imagine a high spin, low spin kind of metal. You might want to smoothly go from one to the other. You might actually want to have a linear combination of these electronic configurations, and that's by construction not possible in Hartree Fock. And so whenever it comes to that, so high spin, low spin, bond dissociation, carbines, also this is a problem for Hartree Fock. So in the Hartree method, you have a product ansatz for atoms. So let me step back. Before we introduce the Hartree Fock method, we will talk about the Hartree method. Okay, the reason is that Hartree Fock, you can view Hartree Fock as a correction to the Hartree method, but to appreciate that correction, of course, you need to familiarize yourself first with the Hartree method. So within the Hartree method, you write the Hamilton operator for an n-electron system, right? So imagine one atom, right? And it has a lot of electrons, so n electrons. So this is how you would write it. This is the kinetic operator, right? This is the external potential, so just your distance, the distance of electron I from the nucleus. That's the nuclear charge of your one atom. And then you have the electron-electron repulsion operator, okay? So that's a Coulombic repulsion operator. So just because of this inter-electronic repulsion operator, you cannot really write the Schrodinger equation as a product of wave functions for every electron. Right? So that's what's so annoying about this inverse Coulomb operator, right, for the electrons. Now, the Hartree method simply approximates that away. It says, yes, we can, right? When in fact you cannot, formally you cannot, but arguing that within perturbation theory, we simply do a product ansatz for our first order wave function, where we say now we have basis functions for every electron, and our total wave function is a product of these guys, right? So, and we actually say these F orbitals, these are just hydrogenic atomic orbitals. So is the solution to your Schrödinger's equation for the hydrogen atom. You have your angular momentum, y, and your radially dependent function, r, okay? And you have all the quantum numbers as indices. So the Hartree method presumes that this is an okay ansatz, right? And basically what we will see now is that this fails horribly. So this is, if you have ever wondered, right, why we don't do that ansatz, why can't we approximate our wave function simply as a product of atomic orbitals? That is basically the reason why. You can always refer to the Hartree method, which tries to do that. So you would then fill the ground state of the atom with two electrons with opposite spin, right? Because of Pauli, you would fill in the lowest orbital one after the other, and when you reach n, right, then you have the electronic ground state configuration. Now, this total psi here then is qualitatively useful, right? But it does not reach a quantitative predictive power. Okay. These basis function here, they contain the nuclear charge Z. And as we've seen in perturbation theory, if instead you use an effective nuclear charge, you get some screening here, which improves the description, but it's still not quantitative, of quantitative accuracy. So you can also then go beyond just these hydrogenic wave function and plug in whatever function you wish, right? Whatever has the shape, let's say thousands of Gaussian functions and so on, and you modulate their shape such that you minimize according to the variational principle, right? But typically we presume that there's just a radial contribution from the hydrogenic atomic orbital. So the Hartree method then is really this this idea that and it was introduced by Hartree, that you rely on this this product ansatz, and you can really find that you get the best possible product function through the variational principle as we discussed it. So you can guess a product function in the beginning, right, which is this product of these S functions now, where this is some normalized radial function, and then you multiply it with the spherical harmonic to get the to recover sort of what looks like the atomic orbitals. You then consider the electron 1, which gets repelled from electron 2 because of its fixed electron density, right? So that's basically this S2 squared in with this distance, right? So this is the repulsion, and if you integrate then over all possible over the entire volume of electron 2, right, then you get the interaction between your electron 1 and the entire electron density of electron 2. And this means then it's basically this term here, the integral over dV2 times this Coulomb potential. So if you add this up, right, for all electrons now, right, so that's the sum here, then you contain the potential of all electron densities of the other electrons that act on electron 1. So this is the potential acting on electron 1. This is the electron density from all other electrons, and this is the nuclear charge which attracts you. So they have these two terms at opposite sign, right? Now, within the central field approximation, you can presume that the effective potential that acts on an electron in an atom, that this potential is spherical. So it does not depend on where you are, right? In terms of the potential, right? Not how the wave function looks like. And so this means you can average out the angular dependency. So in your S here, which still contains your spherical harmonics, right? That drops out, and so basically your integration, you get this changing from spherical to radial coordinates, right? Your integration then changes like this. So as a next step, we use this V1, right? This is our potential now for our electron. We use this in a one-particle Schrodinger equation. So this is now our potential, and note that this potential contains the electron density from the other electrons, right? So it's sort of nested, right? It must be something recursive we have to do here. So it's like a hen and an egg problem. But let's assume that, right? This is something which you haven't seen yet in any of the chapters we've discussed so far. And this potential is now supposed to work on an orbital here for electron 1, where we presume this T1 here is a better orbital for electron 1 than S1 used to be. Okay, so if we can solve this, right, and we need for V1, of course, all the other S functions for all the other electrons, but then we can do this for the first and the second and for all other electrons, right? So we move from a bunch of orbitals which we labeled as S to a bunch of orbitals which we label T. But for solving this, we needed S, right? To get to T, we needed S as an input. Right? And now, if you do that, if you solve that though, then your epsilon 1 would be the energy of this orbital, right? The eigenvalue. In T1, right, because the potential is spherically symmetric, we would expect for T1 again that we can simply have a multiplicative spherical harmonic imposing the radial dependency on the solution. So this means the radial factor in T1 is what you want to get. And you can then write the Schrodinger equation. So this Schrodinger equation here as in equation 5 here. And this is very similar to the hydrogenic atom, really. Right? So what the Hartree method accomplishes is basically it recasts all the electrons of your atom in terms of a whole bunch of hydrogenic electrons, right? And then what's different basically from the hydrogenic atom is the potential which now accounts here, this V here, this is no longer the V of the hydrogen atom, right? This is the V containing all the other electrons in the atom. Right? So V contains the electron repulsion to all others and the nuclear attraction. So this gives us a set of solutions, and the number of nodes, as always, correlates with the energy, and we can define a quantum number here as we go through these solutions with corresponding eigenvalues. From this set of solutions, we take those that correspond to the hydrogen orbital, which we want to improve. So when electron 1 is a 1s electron, right? Suppose in an atom like beryllium, right? Then we take that solution which improves on the 1s orbital. So that comes closest to this, right? So in this case, for instance, the one with nodal, the number of nodes being 0. And so this you repeat for all other electrons, right? So now you go to the second electron, and then you need the s orbital from the first, and then third, fourth, fifth, and so on, to get the new t orbital for the second, and then for the third and the fourth, and so on. Right? So you go for all electrons until you have for all electrons now a new orbital t, right, which has improved your solution. And now you repeat the whole thing. You go back to electron 1, and you get a new bunch of orbitals, right? So from T, let's call them G, right? No, from T you get U, and so on, and you continue until your solutions, right? That means your eigenvalues and the coefficients in your results, until those do not change it. And it is this procedure, right, that you basically solve Schrödinger's equation over and over, every time updating the potential up here. This is what's new in this chapter. This you haven't seen yet in this course, right? And this is one of the key components in modern computational chemistry. It's also known as the self-consistency cycle, right? So, and it comes from this idea that in your potential for your Schrödinger equation, you already include some preliminary representation of the other electrons, and this preliminary information gets updated and improved every time you solve it, and so you can do this until things are converged. Okay. So when everything is converged, the energy of the atom is not simply the sum over the eigenvalues, right? So this is one of the consequences. It's not like in Hückel. You cannot simply sum up the eigenvalues, because for solving this, you included some interactions, right? And so it's not simply a sum over term, right? So you do have some coupling, right? If you had some the product ansatz and no SCF, that would be like Hückel, right? Then we'd have to guess some reasonable input Hamiltonian and the solution, and it's basically fixed and rigid. We cannot improve on this. But by doing this consistently in this iterative manner, you do introduce some coupling that goes beyond your simple product ansatz, in the sense that you get the best possible product ansatz. Okay, I think this was also shown here. So you can show that the best possible product function is being generated by Hartree Fock. Okay. So it's not as bad as that, right? So you have to, in particular, you have to account for some double counting then of your final solution, and this is basically what you see here. So you take your orbital eigenvalues and you subtract contributions from the electron densities interacting of I and J, right, over the distance, right? So this coupling term, and this is basically something like an electron repulsion. You can see this, right? This is an electron density of electron J and this electron I over the distance, right? This is a Coulomb repulsion, and we like to give the symbol J to this Coulomb repulsion term, right? So it's just a notation here, this J. Now we do have some quantum numbers though in the hydrogenic basis functions, and so we can use this in the usual way. So orbitals with the same n and different L, they belong to the subshell, right? And you can also consider an electron density with 2 electrons per orbital. So your rho would be 2 times this G. Actually, I think this G should be squared here. I'm sorry, this is an error here. And so a G is H times psi. This is when you sum over your L's, right? The H is can actually get out here, and you can write it over your spherical harmonics. So this is a theorem here where you don't have angular dependency as long as it's as long as the shells are closed or half filled. There's something known as the Unsol's theorem, and this will generate also electron densities which are spherical. Okay. All right. This is the Hartree method, and in the next chapter here, so this is the part of the introduction, right? And in the next chapter, we'll see that this is not good enough. And one, maybe the main reason why this is not good enough is the spin of the electron, right? So what you really need then to account for spin are the spin space functions, okay? So as you know, electrons are fermions, right? And you know this from experiment. So the most famous Stern-Gerlach experiment proves that, right? That this is how nature was made. So spin is a variable without a classical correspondence, but it is present, right? And so we have to account for this, right? And the way we do this is that the many body wave function must be antisymmetric with respect to exchange of some coordinates, and that includes space and spin, right? So if these coordinates are x, right, if you flip one x with another, your wave function has to change sign. So that's written here. You're flipping now xi and xj, and so then this has to induce this change. And this is a tricky thing because there's no correspondence principle for spin, so we don't have an operator for this, right? The electronic Hamilton operator does not contain spin. So it must be somehow imposed, this behavior, through the choice how we approximate our wave function, right? So it's inherent in this wave function. And so formally, it's actually quite straightforward to account for this. So you can include some spin functions. Let's call them alpha and beta for up and down, or plus or minus, or whatever. And they should be orthonormal, of course. So the inner product with themselves is 1, and with each other is 0. And now the spatial orbitals, they typically form an orthonormal set. And so if this set is complete, as we discussed in the second chapter, any arbitrary function could be modeled by a linear combination of these functions, so by some series expansion. But in practice, of course, we don't have infinity, but a finite set. And so it's only within certain restricted spaces that we can get reasonable predictions. And now if we define a spin orbital, right, then we can combine space and spin into one function, right? So basically you form the product of your phi in space here, right? You take that product of the phi with your alpha or your beta, right? So if alpha is up, then you have your up. If there's alpha, then it's your up electron, and if it's beta, then it's down. And so there are 2 n orthonormal spin orbitals then, which you can construct this way, right? And the alpha and the beta will then in this inner thing take care of this orthonormality, and so that's how you can do it. And if you now go towards the atomic, back to the atom, right? Then we would see that until now, spin and Pauli's exclusion is you only have taken care of it by saying that there can be no more than 2 electrons per orbital. So basically Hund's rule, right, or the Aufbau Principle, right? And that's how we have taken care of it. But in 1930, so Fock and Slater argued that the true wave function needs this explicit spin, and so that it should be antisymmetric. This means we need a linear combination of these chi guys, right, which obeys equation 8. And this is this was the challenge at the time. Nobody could think of something, and this was the main job of Hartree Fock is to accomplish this. So if you have a linear combination of spin orbitals which is antisymmetric, then doing a Hartree SCF with this, this is what we call a Hartree Fock calculation. Okay. And the solution to this question is what's known as the Slater determinant. So the Slater determinant, so this was Slater's proposition, right? So in hindsight, it's a bit surprising that it's called Hartree Fock and not Hartree Fox Slater. But this is the key ingredient here is that your phi, you write your full wave function as this expansion here, okay, where this G12, these are your various terms, right? And this is the same as this Slater determinant, right? So these G12, 11 and G12 and so on, they are the product of your space function times the spin function, right? And so you have this for 3 electrons in 3 orbitals, right? So this is your number of orbitals versus number of electrons. These are the 2 axes. And then you occupy these orbitals in different, so this is the 1s alpha, 1s beta, 2s alpha, okay? And you populate them with different electrons, up to 2s alpha populated with 3 and 3, electron 3 and 3. And this is the 1s alpha occupied by electron 1 and 1. And you can, of course, also consider the combination of the 1s alpha populated by electron 3 and 3, right? And so you see all the possible combinations. And if you make a determinant from that, you get a linear combination, which looks like this. And if you now flip signs, if you now flip indices of electrons, you will see that this phi, equation 30, will flip its sign. Okay, so it meets this condition, condition 8. Now you do an SCF with this expansion, right? And then you're doing a Hartree Fog. You do the SCF just as we discussed for Hartree, and then you're doing a Hartree Fog solution. Okay, I'd like to stop now. We reached the full hour, and tomorrow we continue with Hartree Fog, and we see how far we get. Okay. Are there any questions at this point in time? If not, I thank you for your attention, and I'll see you tomorrow.
Bye.
Bye-bye.